Hello everyone, welcome back. In this video, we'll be taking a look at the sequential criterion for functional limit. So the sequential criterion for functional limit is a pretty useful theorem. So remember that we spent a lot of time working on sequences, where we spent a lot of time proving theorems involving sequences and all, and now we have just moved to this new world of functions. So we were in the sequences world before, now we're in the functions world. So the sequential criterion of functional limit. So this theorem says that the limit of f of x equals to L as x approaches a, which is a functional limit, is exactly equal to for all sequences a n approaching a. We had x approaching a here, but we have all sequences a n approaching a. The limit of f of a n is equal to L. So let's take a look at this graphically to see what it means. So if we have this function right here, and we have a, and here we have L, and this is f of x. So the sequential criterion basically says that if we have sequences for all sequences a n approaching a, for example, we have a sequence a n right here with a1, a2, a3 approaching a, which is tending to a, converging to the a, and we have another sequence here bn also converging to a with b1, b2, b3. So for all sequences an or bn converging to a, we have that f of an also converges to L. So the terms in the sequence are so close to each other, it's as good as drawing a line. Also approach to L. So this is a pretty useful theorem here. So remember that we spent a lot of work in the sequential world. So this theorem says that and now we're in the functional world. So this theorem says that the sequential world and the functional world are exactly the same. The limit of the functional limit is exactly equal, is the same as a sequential limit. So this is a pretty useful theorem for us. It bridges the two worlds between sequences and functions. So let's do the proof of this theorem. So I'm just going to write the theorem again here in red to see, so we can just refer to it again. It says the limit of f of x as x approaches a is equal to L if and only if. So this is a if and only if proof. For all sequences an which tend to a, f of an is equal also, so limit of f of an is also equal to L. So let's do the proof of the first direction. So hopefully it's the easy direction. So first we always assume the first statement. So we assume that limit of f of x is equal to L. So x approaches a. Now choose any sequence an which approaches a. So we need to show that limit of f of an is equal to L. So assume that limit of f of x equal to L for as x approaches a basically means that for all epsilon greater than 0, there exists a delta greater than 0 such that x minus a less than delta. Then we have that f of x minus L is less than epsilon. And any sequence an tending to a means that for all epsilon greater than 0, there exists a delta greater than 0 such that an minus a being less than delta, then an minus such that, oh no, so this is the wrong thing right there, excuse me for that, sorry about that. So this means that I got confused right there. So for all epsilon greater than 0, Remember, we're working with sequences. Sorry about that. So sorry. There exists a n such that for all n greater than n, an minus a is less than delta. Alright. So we need to show the limit of f of an is equal to L. Well, if we combine these two statements, that's what basically means. It means now if we combine those two statements, we have f of an minus L being less than epsilon. Well, let me explain what happened there. So we have that as delta becomes smaller and smaller right here, x is approaching a. So as x approaches a, f of x approaches L. And right here we have that as delta becomes smaller and smaller, an approaches a. Instead of x approaching a, we have an approaching a. So x is replacing an. So, or an is replacing x. So as x approaches a, we had f of x approaching L. Right here we have as an is approaching a as delta becomes smaller. So automatically we'll have f of an will approach L. Since x approaches a, f of x approaches L. So as an approaches a, f of an automatically approaches L. And we're done with the proof of the first direction. So let's do the second direction. Since the first direction was the easy one, this will be the more challenging one. So I'm going to draw a line there. So assume all sequences, for all sequences an which tend to a, and none of these sequences equal to a, because that's the technicality we had and the functional limits, remember? So limit of f of an is equal to L, then approaches infinity. So we want to show limit of f of x as x approaches a is equal to L. So remember, it's always a good strategy to use contradiction when you don't know what's really happening or what direction to head in. So let's use contradiction right here. So suppose for contradiction that limit of f of x does not equal to L as x approaches a. So hopefully, since you're assuming the negation, something strange happens. So this basically means this means we'll negate the definition of it being convergent to L. Since it's not convergent to L, we'll negate the definition. So this means there exists an epsilon greater than 0 such that for all delta greater than 0, there exists an x satisfying 0 greater than x minus a less than delta such that f of x minus L is greater than or equal to epsilon. So using this definition, let's build a sequence of terms, and hopefully the sequence does some strange things. So first, I'm going to say, since it guarantees us that for all delta greater than 0, there exists an epsilon such that this is true. This statement here is true. So let's choose. It guarantees us that it works for all delta. So let's now choose delta equals to 1 over 1. It'll of course work for delta equals to 1 over 1. Then there exists an x. So I'm just going to copy out the definition here. Satisfying 0. Okay, let's say x1 because delta is 1 over 1. So satisfying x1 minus a being less than delta such that f of x1 minus L is greater than or equal to epsilon. So let's make this x1 our first term of the sequence an. So a1 is equal to x1. Now let's choose delta equals 1 over 2. then there exists a x2 satisfying 0 being less than modulus of x2 minus a less than delta, such that f of x2 minus L is greater than or equal to epsilon. And let's make this term x the second term of sequence. Now we're going to repeat it to 1 over 3, 1 over 4, 1 over 5. So I'm just going to say delta equals 1 over n. There exists an x2 satisfying 0. So I'm going to just replace x2 with an, because instead of xn, anyway we're going to write it as an is equal to xn. So I'm just going to replace this xn with an right here, because we're just building a sequence of x which we can call as a also. So an minus a being less than delta, such that f of an minus L is greater than or equal to epsilon. Well, this is a contradiction. This is strange. This contradicts. So let me explain what happens what really happened if you guys don't already see the contradiction. So we have a sequence here, f of an minus L, which is greater than or equal to epsilon, which does not converge. So we have a sequence f of an that does not converge to L, but we just assumed right here that we assumed that the sequence f of an converges to L. So that means at the end f of an minus L should be less than epsilon, because we assumed that the sequence f of an converges to L, but we just built a sequence f of an that does not converge to L. So what we assumed was wrong. What we assumed was wrong. That means we assumed that limit of f of x as x approaches a does not equal to L, and that assumption is wrong because it contradicts. Therefore, limit of f of x as x approaches a is equal to L. So we're done with both the directions of the proof. We're done with the proof of the sequential criterion for functional limit. So this theorem, remember as I said, is a really helpful theorem, and it has several consequences. So the first one is that the limit of f of x as x approaches a does not exist if we have two sequences an which approaches a and bn that approaches a, such that the limit of f of an does not equal to the limit of f of bn. So let's just see this visually. If you have this right here and this right here, and now we have a. So we have this sequence an which approaches a and bn which approaches b, but the limit of f of an, this is f of an, and this is f of bn, this is m, and this is L, and L is not equal to m. So that's what so the limit does not exist. So the limit of f of x itself does not exist. So this is called convergence or the non-convergence corollary or criterion. So now let's see an example of this in action. So show that the limit of sine of 1 over x as x approaches 0 does not exist. So let's choose two sequences. Let me choose an as 1 over 2 pi n. So we have to choose two sequences an and bn which both approach 0, which both converge to 0. So an over 2 pi n certainly converges to 0 as n becomes larger and larger, an becomes tends to 0. And let's choose this bn as 1 over pi over 2 plus 2 pi n. So this sequence also converges to 0. So we have two sequences an and bn that both converge to 0. But the limit of f of an, which is sine of f of an is basically sine of 1 over a of sine of an, which is sine of 1 over an, which is sine of 1 over an, and 1 over an is equal to 1 over 2 pi n. So this is sine of 2 pi n, And remember, sine of 2 pi n is 0, and sine of 1 over bn is equal to sine of 2 pi n plus pi over 2n, because we reciprocate pi over 2, we reciprocate the numerator and denominator. We have that sine of any pi over 2 is always equal to 1. So we have two sequences an and bn which converge to 0, but f of an is equal to 0 and f of bn is equal to 1, which are not equal to each other. Therefore, limit of sine of 1 over x as x approaches 0 does not exist. So this is a nice way to show that a limit does not exist, instead of the old-fashioned way of showing the definition, of using the definition. So another consequence, or another nice thing that happens, is the algebraic limit theorem for functions. So remember that we had this also for sequences. Now, using the sequential criterion or for functional limits, we can just transfer whatever we learned and whatever we proved to the functional world without having to prove them all over again, because the sequential criterion tells us that these two worlds are exactly the same. The functional world is just the sequential world in disguise. So we have the same things we had for sequences, but now for functions right here. So let's see how this theorem, how the sequential criterion makes it easy for us to prove this. So in red here is the traditional way. So all this in red is the traditional proof, without the sequential criterion for this, for a part of the algebraic limit theorem. So we do it the traditional way. For all epsilon greater than 0, there exists x minus c less than delta, such that we need to show this is true. And we know that limit of f of x equals to L and g of x equals to m as x approaches c. So there exists a delta 1 such that f of x minus L is less than epsilon over 2, and a delta 2 such that g of x minus m is less than epsilon over 2. Then we choose the delta equals to minimum of delta 1 and delta 2. And then we use the triangle inequality right here to split this big one. We have to remember show that this right here is less than epsilon, so we split it using the triangle inequality and show that it's less than epsilon over 2 plus epsilon over 2, which is equal to epsilon, and we're done with the proof. But that's the traditional way of showing it. That's the longer way of showing it. We've already shown this. So if you've noticed, the proof of this is pretty similar to the one we did for the sequences. So since we have already shown it, it's inefficient to do it all over again. So we're just going to use the sequential criterion to show that, to prove this. And the sequential criterion says that proving that limit of f of x plus g of x is equal to L plus m is equivalent to showing the sequences f of xn plus g of xn tend to L plus m as xn tends to c. So we know that f of xn tends to L and g of xn tends to m, and remember that f of xn and g of xn are just sequences. These are sequences, and we already know that for sequences, when you add sequences, the limits, you just add the limits. So when we add these two, it's just we add the limits, and we know that f of xn, the sequences f of xn and g of xn are just equivalent to f of x and g of x as x approaches c. So we're done with this proof. So if you notice here, this proof is pretty much shorter than the one we did here, and we don't need to do all the work we did as we did for sequences all over again. We can just use the sequential criterion to transfer all that knowledge we had for sequences all the way to the functional world. So hope you guys enjoyed this video. See you next time.